We'll wait for a few minutes for others to join. All right, welcome everyone to week 12 of the tutorial of thermodynamics. And we are towards the end of our tutorial series. of this Nptel course, Thermodynamics. I hope everyone is regular to their lecture videos, uh, which are provided on the Nptel portal to all of you, as well as you are ready with your assignments, regular with your assignments, and you're ready for the exam, which is going to be conducted very soon. And probably this will be our last session, and hopefully I have covered all the topics. Today we'll be pondering over a few left out topics, and then we'll start with questions as well. Okay, let me share my screen and let us start. Okay, I think my screen is visible. Yes. Okay. Cool. Yes. We are perfectly. So in the last class or tutorial, we discussed about the last topic was Joule-Thomson coefficient. Okay. So what was Joule-Thomson coefficient? Which is nothing but slope of temperature to that of pressure for an isenthalpic curve, isenthalpic process. Right? And we have also proved that value of Joule-Thomson coefficient for an ideal gas is 0. As well as we have also proved that enthalpy and internal energy of an ideal gas is a function of temperature only. But for real gas, it is function of temperature as well as pressure and volume respectively for enthalpy and internal energy. Okay. All right. So today I'll do the next topic, that is inversion curve. Let me write it down. So what is an inversion curve? Basically, it is a curve that is being generated by joining the peaks of different isenthalpic curves on temperature pressure curve. So we knew that the mu J, that is the Joule-Thomson coefficient, give us the rho T by rho P at constant enthalpy. Okay, rho T by rho P at constant enthalpy. So it's the temperature pressure plot slope is nothing but your Joule-Thomson coefficient for isenthalpic curves. And when you draw multiple curves like this, for the constant enthalpic process, then you can say that the peaks of the curves forms a inversion curve. So what is the significance of an inversion curve basically is, if you want to know for a refrigeration cycle, that is your vapor compression refrigeration cycle, which kind of refrigerator you want to use, then this curve plays a very, very important role. Because in a VCRS cycle, vapor compression refrigeration cycle, there is a process that is an isenthalpic process. Okay, isenthalpic process where the pressure and temperature is required to be dropped. So I'll give a rough figure like this. So this is a compression, condensation, this is an isenthalpic. That is nothing but your throttling process. Okay, in terms of that, this process, and this is evaporation. So 1, 2, 3, 4. So from process 3 to 4, this is a throttling process where your pressure as well as temperature has been decreased. Okay, pressure as well as temperature has been decreased. So what kind of refrigerant you want to use in that refrigerator or refrigeration cycle, this curve helps a lot to know. So let me draw an inversion curve first of all. Okay. So this is temperature axis. This is pressure axis. Suppose you are at a state 1. Suppose this is your first state. Okay, this is pressure 1, temperature 1 for you. All right, P1 as well as T1. Now, during the throttling process, as you know that pressure decreases. Okay, but also temperature eventually increases first. Pressure decreases and temperature increases. Pressure, if you see, the pressure has dropped, but temperature has gone up. So suppose this is your state, P2 and T2. So your pressure has decreased and temperature has increased. All right. Carefully understand this curve. Then, as it's a throttling process, your pressure will significantly try to decrease, but now temperature will also decrease. Temperature will also decrease. So pressure decrease and temperature also decrease. So this is P3, T3. Now the question arises, why during the throttling pressure is always decreasing from P1 to P3, okay? But why first initially temperature increased and then it decreased, okay? The reason is that throttling is a process which we have already discussed. It's a restrictive process. You are passing your fluid or refrigerant through a restrictive passage. So due to the internal friction, initially the temperature rises up, but later on the temperature drops down. So that is your throttling process, okay, where pressure and temperature finally decreases. Eventually it increases, then decreases. Okay. So this kind of curve, this complete curve for one of the refrigerant for a constant enthalpy, because it's an isenthalpic process, and throttling is an isenthalpic process. This is your isenthalpic process from point 1 to point 3 or whatever you want to the final state. This is what one of the refrigerant. If you want another kind of refrigerant experiment, so it will go suppose like this, okay? Then another kind of experiment for another refrigerant, it will suppose go like this, okay? So all of these are the peak of this refrigerant, of these curves, okay? And the curve formed by joining the peaks. These are the peaks. Joining the peaks. Okay, these are the peaks. If you join the peaks of all these curves, that curve is called as inversion curve. That curve is called as inversion curve. I hope it's clear now. Okay, so I'll make a better visual representation of a diagram now. This is your first curve. This is your second curve. This is suppose a third curve. And all of these are the peaks of the curve. Okay. Every of that has h is equal to constant. This is equal to constant. If you join the peaks of this curve, okay, then this curve is known as inversion curve. So this curves help us to know that what kind of refrigerant we can use, where we can get maximum possibility of dropping the temperature so that we can have we can choose what kind of refrigerant we should use. I'll relate it to the mu J, that is Joule-Thomson coefficient. First, let me write that. So all of these are the peaks. This, as well as this. All of these are the peaks. Okay. So if you observe here, take initially the process got from this side to this side. Okay, this side to this side. So let me write here. It is inversion curve is the curve generated by joining peaks of different isenthalpic curves on temperature pressure plot. Okay. So this right-hand side of the inversion curve, this side of an inversion curve is the right-hand side. This side of the inversion curve is the left-hand side. So let us observe what is happening. Right-hand side, that is the outside of the inversion curve. Right-hand side, first I'll talk about the right-hand side. This is your right-hand side, or the outside of the inversion curve, is the region of heating. So if you observe from state this to state this, or if you say till state this, your temperature is eventually rising up. Okay. Although pressure is decreasing, but temperature is rising up because, as I've explained, because of the internal frictions. Okay, due to the restrictive passage. Because entropy, uh, throttling is a process of passing through a restrictive passage arc, which maintains the constant enthalpy. So here, due to that restriction, internal friction happens, because of which the temperature rises. So initially, the temperature rise up. Okay, the temperature rise up. So outside the inversion curve is called a heating zone. Let me write here. It's called heating. It's called heating. Okay, and have a negative slope. How? If you observe, this is the slope d dou t by dou p for a constant enthalpy curve. Any of the curve is the slope. This is a mu j, that is Joule-Thomson coefficient. So if you observe, if your process is going from state this to state this, okay, state this during the heating process, So here your slope is dou t by dou p for a constant enthalpy. So temperature is rising. So final temperature is higher than the initial temperature. That means it's a positive value. Whereas pressure is dropping. Final value is less than the initial value. So that is negative. So positive or negative is eventually a negative value. So slope is negative. Your Joule-Thomson coefficient is negative. Okay. I'll say this process goes from O, A, B. Okay. And this is O2. This is O2. Okay. Your inversion curves look like a frame, a better, sorry. This is your inversion curve. Okay. It's bold and metal. And inside is your cooling region. Inside the inversion curve is your inside, that is left hand side. Okay. This is your cooling region. Whereas out inside inversion curve is cooling region. Okay. And have positive slope. Positive slope. If you observe from state A to state B, so this is your curve. Uh, This is your state A to state B. So here, if you observe, temperature is dropping as well as pressure is also dropping. So your slope rho T by dou P for a constant enthalpy is temperature is negative, final temperature is less than the initial temperature, final temperature is less than the initial temperature, so negative value, as well as pressure is also dropping, final pressure is less than the initial pressure. So negative by negative is your positive value. So slope is positive. Okay, slope is positive. And you know that for the state position A, for the position A, if you see at this, the slope is zero. Slope is zero. And when dou T by dou P is zero, for which refrigerant? If you say you want to use air or an ideal gas, we generally treat air as an ideal gas. So ideal gas has a slope zero because we have proved last time also in the last tutorial that Joule-Thomson coefficient, which is nothing but the slope dou T by dou P at constant enthalpy, is zero for an ideal gas. So you can never use air as a refrigerant in a vapor compression refrigeration cycle. Apart from that, you can use different refrigerants, and you can know that if the temperature that refrigerant is effective if it falls inside the inversion curve. Okay, inside the region of the inversion curve. Okay. All right. So if we say this inversion curve probably go up to any of the value, this is suppose if I extend this axis. So this is a maximum value of the inversion curve at temperature. Okay, and that is the maximum of that inversion curve point as well. So if your temperature always fall inside the region and below this maximum, so suppose it falls here, it falls here, it falls here, then you can use that refrigerant because it is used for cooling purpose. Refrigerants are always used for cooling purpose. I hope now the inversion curve concept is very, very crystal clear. So inversion curve is generated by joining peaks of different isenthalpic curves on temperature pressure plot. If that is your green plot, outside the inversion curve is a heating because the temperature increases, pressure decreases, negative value of the slope. Whereas inside the inversion curve is a cooling region and has a positive slope because pressure as well as temperature both decreases. So you can say that in summary, mu J is equal to dou T by dou P at constant enthalpy is less than 0, equal to 0, and greater than 0. So if it is less than 0, negative slope means heating purpose. Greater than 0, that means it is for cooling purpose. Equal to 0, that means it's an ideal gas. Okay. I hope that is clear. Any doubts? Just give me a note, please. Yeah, sorry. Okay. So mu J less than equal to greater than. So I can also write here heating region, cooling regions, an ideal gas. Okay. I hope it is very, very clear what inversion curve is. We have discussed the Joule-Thomson coefficient as well. Any doubts? Okay. If it's clear, let's move on to the next topic, that is Clausius-Clapeyron equation. Okay. Clausius-Clapeyron equation. Clausius-Clapeyron equation. So what it is basically So it's an equation in a thermodynamics that describes relationship between vapor pressure and temperature of a pure substance during a phase transition. Okay. So what is the relation between vapor pressure and temperature of a pure substance during a phase transition? So again, we want dou P by dou T kind of relationship during the phase shift. Okay. So like liquid to gas, solid to liquid, or solid to gas, whatever. So let me write here. It is equation in thermodynamics that describes the relationship between the vapor pressure and temperature of a pure substance during a phase transition. Like liquid to gas, or you can say solid to liquid. All right. Okay. As I've told earlier also, in the wet region, pressure and temperature are independent of volumes. Okay. Pressure and temperature are independent of volumes. Okay. So in case of wet region, pressure is constant and temperature are constant are same. Okay. Let me write here. And you don't apply PV is equal to MRT, that is ideal gas equation, in the wet region. We have explicitly stated in a very bold note, okay, about that. So in case of wet region, pressure and temperature are independent of volume. So from one of the Maxwell relation, which we derived from the four Maxwell relation, if we come to one of the Maxwell relation, from relation that is dP by dt at constant volume is nothing but ds by dv at constant temperature. So what can you write? Entropy. Entropy can be written as dq by t. Okay, dq by t. dq by t, that of dv at t. Since you know that dq is equal to tds. Okay, and in the wet region, what is dq? As for constant pressure in wet region, you know the plot, ts plot in the pure substance which we did. So pressure is constant, and we are talking about wet region. Okay, you know that it is nothing but change of enthalpy, mass into change of enthalpy, dq can. Okay, so dq is dh minus VdP. So entropy is 0 in constant in wet region. Okay. So dq is nothing but dependent over the enthalpy. So you write here dq is mass into hfg. F and g are the enthalpies for saturated liquid and vapor. So hfg is hg minus hf. Okay. By t dv. Okay. All right. T dv. And m into hfg can be written as complete hfg. If we say hfg by t dv, that is your dp by dt. So therefore, hfg can be written as, so final relation is dp by dt for a constant volume is equal to hg minus hf to that of t. dv can be written as vfg. So vg minus vf. So this is state f, this is state g. Okay, state f, state g, hf, g. Draw a box here and keep this thing in one of the box. Okay, so this is your final relation that relate what do you say, that pressure and temperature. Okay, relation between vapor pressure and temperature of a pure substance, that is nothing but hg minus hf to that of t into vg minus vf. A very important relation. It's talking in the wet region. Also, since value of vg is much greater than vf, so gas has a much higher value than the saturated liquid. You can say that, you can ignore. So Vg minus Vf can be written as Vg only. Okay. Put it back in the above relation. So you get dP by dt at constant volume is Hg minus Hf to that of T into Vg, specific volumes. This Vf and Vg all are specific volumes at saturated liquid state and saturated vapor state. Now, if I want to go beyond the wet region, then you can apply the ideal gas equation in the superheated region. So apply PV is equal to MRT. For saturated vapor region and not for wet region. So if I say that, I can write P into V by M is equal to RT. So a specific volume is PV is equal to RT. Okay. So this implies specific volume is RT by P. And this I'm talking about which state? In this saturated vapor region. Okay. So that is VG I'm specifically talking about. So that is but nothing but your V of G. So put that V of G in above relation. So you get let me write here in vapor region, saturated vapor. Okay. Put that Vg back. Dou P by dou T constant volume is nothing but HgF by TVg. Hg minus Hf by T Vg, and put this Vg here. So you get that HgF is nothing but HFG is nothing but latent heat. Okay, by T, and it is RT by P. Okay, so is P into latent heat by RT dP by dt constant P into latent heat by RT square. So this is your final relation of pressure and temperature change. Okay, for any of the impure substance during which is going through a phase change. Okay, I hope it's clear. Very well clear. No doubts. So we are quite finished with our notes and everything. Now let's do some questions. I hope you all are ready for the questions. So I'll be taking pretty standard questions, which has been asked in various competitive exams also. I'll be taking very standard questions, okay, in good books. So let's start. Okay. Consider a mixture of two ideal gases. X and Y with molar masses 10 kg and 20 kg per kilomole. Respectively in a container. The total pressure in the container is hundred kilopascal, and total volume of the container is 10 meter cube. And the temperature of the contents of the container is 300 Kelvin. Okay. If the mass of gas X in the container is 2 kg, then the mass of gas Y in the container you have to answer. Mass of in kg. Okay. You can assume that universal gas constant is 8.314 kilojoule per kilomole Kelvin. Okay. Yeah. Do it. Take few minutes and do it. Okay, I guess most of you have done by now. So it's a pretty simple question. There is a mixture of two ideal gases out there that have molar masses 10 and 20 kg per kilomole. And total pressure inside a container is given to you. Total volume is given to you of that container, and what is the temperature inside that container. So if it said that mass of the gas X is known to you, that is too easy. You need to find out what is the mass of gas Y. Pretty simple question. Let us do solution. Let's draw a container first of all. Suppose you have a container here. It's an insulated. Suppose there's no heat interaction. You can assume that thing. So there is gas X, there is gas Y. Okay. So mass of gas, molar mass of gas X, that is capital X M, is nothing but 10 kg per kilomole. Okay. And it is also given that mass of that X is 2 kg. Molar mass of gas Y is given as capital My, that is 20 kg per kilomole. And you don't know what is My. Okay. You need to find out smaller. So if you use the ideal gas law, because these are ideal gas. So from ideal gas law, PV is equal to nRT. Okay. All right. So N is that total value of that gas in that total value. So you know what is the total pressure? It's given as 100. All right. It's given as 100 kilopascal. V is given as 10 total volume. And suppose it's a total number of, okay. And capital R is 8.314. Okay. Universal gas constant. And total temperature is given to you 300 of that. So if you solve it, N comes out to be 100 into 10 divided by 8.314 into 300. So N value comes out to 0.4 from here. And this N is sum of gas N of gas X plus that of Y. Since N is equal to total gas value of gas in a container, that is N of X plus N of Y. And moles is nothing but given mass to that of molar mass of that gas, respectively. So mx, capital Mx, plus my by capital My. So what is mx? It's given 2. What is capital Mx? That is 10. My you don't know. And capital My, you know, that is 20. Now you need to solve. So My by 20 is 0.4 minus 0.2. So My is 0.2 times 20, that is 4 kgs. So that was your final answer. Okay, clear? Any doubts in this? Pretty easy. All right, let's move on to the next question. A steady state at steady state, sorry, at steady state, 500 kg per second of steam enters. A turbine with specific enthalpy equal to 3500 kilojoule per kg. And specific entropy equal to 6.5 kilojoule per kg Kelvin. expands reversibly in the turbine. Uh, in the turbine to condenser pressure. Heat loss occurs reversibly. In the turbine at a temperature of 500 Kelvin. At a temperature of 500 Kelvin with the exact specific enthalpy. And specific entropy are 2500 kilojoule per kg and 6.3 kilojoule per kg Kelvin. Respectively. The work output from the turbine is in megawatt. Okay. Again, a pretty simple question. You can do it. Good, but simple question. Solve it. Okay, I guess most of you have done. Let us do this, solve this question. So it said that there is a steady state. Okay, situation is there given to you. It said that 500 kg per second of steam is entering a turbine. So at a specific enthalpy is given, specific entropy is given to you. It's a reversal process in the turbine. Again, it's an open system because it's a we are talking about a turbine. It is not a complete. It's an open system device. Okay, and there's a heat loss which occurs in the turbine at a temperature of 500. Specific exit enthalpy and entropy are given to you, and it is asked that what is the work output from the turbine. So it's basically the concept of useful work which we have done. Okay, so for open system, what is a useful work? It is nothing but H1 from one state 1 to state 2, difference of enthalpies minus T naught into S1 minus S2, whatever the surrounding temperature is. So let us do. Suppose this is the turbine given to you. So this is state 1, and from here it exits state 2. Okay, this is a turbine. All right. So whatever mass enters, mass flow rate is nothing but 500 kg per second. Is given to you. State 1 enthalpy, specific enthalpy H1 is given as 300 kilojoule per kg. State entropy, specific entropy S1 is given as 6.5 kilojoule per kg Kelvin. Okay, 6.5. Also, state 2 enthalpy is given to you, that is 2500 kilojoule per kg. And entropy is given to you 6.3. Okay. Surrounding temperature is given to you as 500 Kelvin. Okay. Now work output from the turbine of turbine, or you can say useful work of turbine is nothing but H1 minus S2 minus T naught time S1 minus S2 S H initial minus H final minus T naught into S initial minus S2. All right, that was a pretty simple thing which we have already discussed in our previous. Okay, so have I written values to be wrong? Oh, H1 was 3500. Sorry. Secondly, I wrote 3. So that is 3500 minus 2500. T naught is 500. S1 is 6.5. S2 is 6.3. Okay. So this comes out to be 900 kilojoule per kg. That is work by turbine. Now the power output has been asked. Power output is mass flow rate into work of turbine. So power output in megawatt. Power of turbine is mass flow rate into work of turbine. So mass flow rate is 500 and it is 900. Okay. It is 45 into 10 to the power of 4. You can say it's kilowatt. And they have asked in megawatt. So it is 450 megawatts. If you divide by 10 to the power of 3, 450 megawatt power of turbine. That is your answer. All right, pretty simple question as I said. Question is very easy. Okay. Any doubts? Okay, no doubts. Then let's come to the next question. A rigid tank of volume 8 meter cube is being filled up with air from pipeline connected through a valve. Initially, valve is closed and tank is assumed to be completely evacuated. The air pressure and temperature inside the pipeline are maintained at 600 kilopascal and 306 Kelvin. Respectively. The filling of the tank begins by opening the valve and the process ends when temperature is equal to the pipeline pressure. During filling process, heat loss to the surrounding is 1000 kilojoule. The specific heats of air at constant, so I can write directly Cp is equal to 1.005 kilojoule per kg Kelvin and Cv is 0.718 for air. Okay. You can neglect the changes kinetic and potential energy. You need to find the final temperature of the tank. Neglect kinetic energy and potential energy. The final temperature of the tank after completion of filling processes. After completion of filling process. All right. I'll zoom it out. I hope this is visible. Okay. Solve it. Okay, I hope everyone has done this question. Pretty simple question it is again. Now you have to identify which topic this question has been asked. So it's related to steady flow energy equation concept. Okay. So it said that there is a rigid tank of some volume which is being filled up from the pipeline. Okay, filled up with air from the pipeline connected through a valve. Initially, valve is closed and tank is initially completely empty. Okay, the air pressure and temperature inside the pipeline are maintained at 600 kilopascal and 300 Kelvin. And when the filling of the tank begins by opening the valve, then the process ends with temperature equal to pipeline pressure. So during the filling process, heat loss is there also. It's not insulated. You can neglect the changes kinetic and potential energy. Then it is asked what is the final temperature of the tank after filling as complete. Okay, after filling is complete. All right, let us frame a solution. Okay, suppose there is a tank. Okay, and it is connected through a valve. This is your valve, and it is said that temperature and pressure inside the pipeline is 306 Kelvin, and pressure is 600 kilopascal. Okay, in the and this is your tank. So if you say that this is your situation 1, and after filling your situation is 2. Okay. So from steady flow energy equation, it is M1H1 plus kinetic energy 1 plus potential energy 1 plus heat transfer. Okay. Is equal to M2 H2 plus kinetic energy plus potential energy plus work transfer. So there is no work transfer. You eventually know that, just a filling process. Kinetic energy, potential energy changes are neglected. So you are just left with M1H1 is plus heat transfer. Okay, plus heat transfer is equal to M2, and H2 is nothing but U plus flow work. So there won't be any flow work later on, because in the filling process there's no flow work. It's only U2 you can see. Okay, M2 U2, because H is U plus PV. Okay, M2 U2. All right. Now M is same. Okay, whatever mass is entered, that mass is exited. So M H1 plus Q heat transfer is equal to M U2 or U final. Okay, so I can say initial and final in terms of that. Initial and final. So M I don't know right now. H initial is Cp times Ti. What is flow? Heat flow rate is not given. It's just heat to the surrounding is given. So that is, so I can write 1000. Okay, because it's heat lost to the surrounding, that's why it's 1000 is equal to M into Cv T final. Okay, so initial temperature is given 306 Kelvin. M you don't know. M into 1.005 into 306 minus 1000 is equal to M into 1.718 T final, which you don't know. All right. So currently M and T final both are unknown to you. Now let us get the mass. Since PV is equal to MRT, okay. So final situation, whatever the volume of the dot is. So M is P final V final by RT final. Okay. So what is final pressure? 600 kilopascal, whatever the pressure is maintained in the pipeline. What is the volume of the tank? Is it given? 8. 8 meter cube. Yes. Initially it is given 8. R for the gases, we know that 0.287 for air. Kilojoule per kilomole Kelvin. And T final you still don't know. But you know what is mass in terms of this. Now you put this mass here. So you can write N. So first of all, let us write like this. 1.005 into 306 is equal to minus 1000 by M is equal to CV 0.718 T5. Okay. Now, or you can write like this equal to and plus. Now you put this M here. So that comes out to be 1000 by 600 into 8. So this value is nothing but, if you solve it out, it is 16724.7 by TS. 16724.7 by TF plus 0.718 TF. So right hand side comes out to be 0.78 TF near about, and left hand side is 1.005 into 306. So TF comes out to be 1.005 into 306 by 0.78. So this is near about 395 kelvins. This is your answer. Okay. It's simple steady flow energy equation concept you have to use to solve this. Next question. Consider adiabatic flow of air through a duct at a given point in the duct. Velocity of air is 300 meter per second. Temperature is 330 Kelvin. And pressure is 180 kilopascal. Assume that air behave as a perfect gas. With CP being kilojoule per kg Kelvin. We need to find out stagnation temperature at this point. At this point. All right. All right. Pretty simple question. You can do it. So from this question, I want to introduce a concept of somewhat say Mach. That's how I've taken this question. Stagnation temperature, stagnation pressure, and what is Mach number? That's why I've used this question. Directly from a question, we will understand this. I'll give you 2 to 3 minutes only to solve this, so that if you know the concept, well and good. If you don't know, then I'll explain. Okay. It is due. So there's a adiabatic flow of air through a duct, and velocity is given to you of that, which is 300 meter per second. Temperature is 330 Kelvin. Pressure is given. Cp is given. Where you need to find the stagnation temperature. Okay. So what do we mean by basically stagnation temperature? It's where the fluid velocity comes to zero at rest. That is a position where stagnation is achieved, and the temperature at that point is the stagnation temperature. Eventually, it moves that way. Okay. So let's do the solution. So what is a Mach number? Mach number is velocity of that uh, velocity of that sound in the medium to that of speed of sound. Okay. So velocity of whatever the particle air is there to that of speed of sound. Okay. So V by, and speed of sound is in a medium is gamma r t. So V is given to you as 300. Gamma is adiabatic, so that means 1.4. R is 0.287 or 287. And temperature is given to be 330. So from here, it comes out to be 0.823, Mach number. Okay, it is 0.823. Now, there is a relation between stagnation temperature to that of initial temperature. So stagnation temperature to that of initial temperature T is equal to 1 plus gamma minus 1 by 2 Mach square. Okay, remember this relation. So stagnation temperature, you don't know. What is initial temperature? You know that. What is that? 330 Kelvin. 1 plus gamma is 1.4 minus 1 by 2. Mach number you have got 0.823 square. So final value is, this comes out to 1.154 into 330 is your stagnation temperature, 374.7. Okay. This is your answer. Hopefully. Concept I want to get through a question only. Okay. All right, let's do the next question. The volume and temperature of air. In a closed vessel is 2.87 meter cube. And 300 Kelvin respectively. The gauge pressure indicated by a manometer fitted to the wall. Of vessel is 0.5 bar. If gas constant of air is 287 joule per kg Kelvin and atmospheric pressure is 1 bar, the mass of air in the vessel is. Okay, you need to find. Pretty simple question once again. Solve it. Okay, let us solve this. Pretty simple question once again it is. So it's given that you are having the volume and temperature of the gas, which is assumed to be an ideal gas, is in a closed vessel is 2.87 meter cube and 300 Kelvin. And the gauge pressure is given to you 0.5 bars. So specifically note that it's a gauge pressure. And gas constant is given, atmospheric pressure is given. It's asked what is the mass of the air in the vessel. So in the ideal gas equation, PV is equal to MRT. So what pressure we use is the absolute pressure. We have discussed this topic, okay, in very detail. So, from ideal gas, from gas law, PV is equal to MRT. So this P is nothing but P absolute, okay? And we know that P absolute is nothing but P gauge plus P atmosphere. Okay, we have drawn this kind of chart. This is a reference state. So suppose still here is your gauge pressure. This is your gauge. Okay. And this is your atmosphere. Till here. And this is your reference state. So P absolute is, this is your complete P absolute. This is gauge plus atmosphere. Okay. So it's given that what is absolute pressure, need to be find out what is gauge pressure. 50 is given, 0.5 is given as the gauge pressure. So that is 0.5 and atmospheric is 1. So it is 1.5 bar absolute. In terms of pascals, kilopascals, you can say that 1.5 into 101.325, that is near about 1.325 kilopascals. So that's your absolute. Now put this absolute back. So therefore, M is equal to PV by RT. Put this here. So P is 151.325. Volume is given to you. That is how much? 2.87 meter cube. Yeah. 2.87. R is 0.287. And temperature is given as 300. So put all these values, you'll get your mass as 5.04 kg. All right. Okay. 5. So we have done quite a lot of questions starting from the initial chapters to the later one till pure substance. So I want to cover this kind of thing so that we have a quick revision in the form of questions as well as new stagnation topic as well, stagnation temperature topic as well. So this is all from our end for the course NPTEL Thermodynamics. So we have covered everything in very detail. Okay. So for all the topics related to questions, topics, discussions in very thoroughness. And probably this was the last tutorial from my end for the week 12. And you guys might be having your exam now. All the lecture videos are already uploaded on the NPTEL portal. I hope you have been regular to your course assignments. And those who have enrolled for the test, I wish you all the very best for your test and exam. Those who want to watch these tutorials, all of these tutorial recordings are available on YouTube, on my YouTube channel. That is, I'll write it here. My YouTube channel is NPTEL with Varnit. So those who have enrolled for the course, they are eventually getting the links for each of the tutorial recording in an Excel sheet by the NPTEL team, as well as the PDF of the Google Drive where I am uploading all these PDFs. Those who are watching on the YouTube for the first time, so it's on my channel, and in each video description of the playlist Thermodynamics, the link for the Google Drive is there, from where you can access these notes. So I wish you all very, very best for your future endeavors. And this was my last tutorial for the course Thermodynamics. So you can reach out to me anytime. My name is Varnit Kapoor. You can reach out to me from any of the social handles. Okay. Thank you so much. Bye-bye.